All right. Did everybody get a copy of the notes? Your next assignment due on Monday is that handout problem, and we're going to spend a few moments discussing that at the beginning of class today, and then problem 42 in the book, which is the nodal problem where there's 3 pipes connected together at a pair of nodes. So I'll take that from you on Monday, and then the next assignment is going to be due on Friday. And this assignment due on Friday is the problems that are related to the Hardy-Cross method. And so you've got some time to continue sort of taking in what we're going to do with the Hardy-Cross/loop method. We're going to continue the example that we worked partially in class on the board last time. We'll keep going with that. But before we do, I wanted to give you some tips on how to solve this handout problem that's due on Monday. What you know is that the head at this reservoir on the left is 25 meters because that's the water surface elevation. So what you can do is you can say that the head at A, H sub A, is 25 meters. There is a pipe connecting the junction to that reservoir, but we assume it's a very small pipe and there's no losses through that pipe. So now we know the head in A, and we also know the head at B. The head at B is 20 meters. What we don't know is the flow rate through each of the pipes. The process that we're going to go through is assume some direction of flow. You just have to make a guess about the direction. And so maybe, for example, you make the guess that you're going to have to check, so don't feel too intimidated about making some guess. Here's C, here's A. What if you assume the flow goes this way, from C towards A? What that would mean is that you can say that the head at C, you can write an equation for the head at C in terms of the head at A. Head at C is head at A plus FLQ squared divided by D2G A squared. And the Q that we're talking about is QAC. So why have I said plus the head losses instead of minus in this equation I've just written on the board? Justin, do you know? If we're assuming that flows from C to A, why would it be that the head at C is the head at A plus the losses? Aaron? Okay. Bert? Yes, in a way. Just by definition, water flows where they're from high head to low head. And so there must be more head at C if the water is to flow from C towards A. Head is just the total energy. Water flows from high energy to low energy. And so if through our guess, we just say we are assuming the flow goes from C towards A. Well, then there will be more head at C than there is at A. How much more head? It's going to be, the difference will be the losses in the pipe. So we can write an equation for the head at C in terms of the head at A. You can also write an equation for the head at C in terms of the head at B. And so if you had assumed that the flow direction was like this, and we know that the head at B is 20. So if the water is going from C towards B, then you'd say that the head at C is the head at B plus FLQ BC squared divided by D2GA squared. And that was a squared, not A2, A squared. That's the substitution we make for V squared, is Q squared divided by A squared. So looking strategically, why do you think we would want to set things up this way, where we know the head at C in terms of the flow through the 2 different pipes? Any guesses on where this is heading? We can. We can say that this term equals that term, and then the other big governing equation we have to help us out is continuity. Continuity must be satisfied. So continuity says that in equals out. So we know that there's 0.2 cubic meters per second coming in, and so that tells us the sum of QBC and QAC. So you can say that QAC is 2 minus QBC. So now you've got two equations, two unknowns. You can find the flow rates. You apply that same process at junction D. Write the head at D in terms of the head at the other locations. But you have to make some guess. And if the guess that you make is wrong in terms of the flow direction, what you're going to end up with is a solution or a flow rate that is a non-positive number, or it may be that you're taking the square root of a negative number, and so you don't have a real solution any longer. So just in summary, this process is we assume some flow direction. Our tool of continuity tells us that any junction, the flow in has to equal the flow out at that junction. And then we're just going to write the head equations in terms of the head at A and head at B. Have you got any questions about that tip that I've given you for the homework? No questions. We will jump back over to the Hardy-Cross procedure. Remember, what happens in Hardy-Cross is that we're simultaneously balancing the flow rate and the energy. In both the nodal method and in the loop method, the main principle that we know has to be true is that you have to have the same amount of energy lost regardless of what route you take between 2 points. And so if water is coming in at this junction, 100, and water is going to flow out at here, this 20. Well, it might be that water goes directly through this pipe, or water can go through here and then through the diagonal pipe. There's multiple routes towards that junction, and there has to be the same amount of head loss through each route. And so the Hardy-Cross procedure is simultaneously making sure that at every junction continuity is satisfied, meaning in equals out, and it's also working to balance the energy so that there aren't these impossible high or low energy paths, that all paths between points have the same amount of energy loss. So this is the procedure that we outlined last time, and I'm going to go ahead and write up on the board to the point where we were previously, and we'll continue because there are a couple of important steps we have to make sure that we take a note of. Duration, loop, pipe, N, R, Q, R times Q times absolute value of Q, N, R, absolute value of Q, delta Q, and corrected Q. Iteration 1, loop 1, pipes, we've got 1, 4, 1, 3, and 3, 4. And then in loop 2, there's pipe 1, 2, pipe 2, 3, and 1, 3. Okay, the n values are 2 for all of them. Who remembers what the n value is for? Ignacio, do you remember what the n value in this process is for? Yeah, why is it 2? Yeah, what does the n refer to? What is that a reflection of? No, it's actually depending on which energy loss method we use. So since we're using Darcy-Weisbach to account for pipe friction, that's why we use 2. But if we had been using Hazing-Williams, it would be 1.85. So in this method, there's some sort of a model that's assuming how energy is lost through the pipes. And since we're using Darcy-Weisbach for that, that's why it's 2. Okay, just to write what our initial assumptions were. There's 100 in here, 20 out, 50, okay. And we called this junction 1, junction 2, junction 3, and junction 4. And our initial guess of flow rates was that in pipe 1-4, we'd have 50, and 50 would go that way. In pipe 3-4, okay, 50, and 1-3, 15. 15, 35. What does this arrow inside with the plus sign refer to? Why have I just drawn that? John? All right. Well, the flow's not going that direction here. Okay. That's right. We're defining a standard notation method, or by convention, we're going to call any flow that goes this clockwise direction positive and against it negative, just like John said. So we've got loop 1 on the bottom, loop 2 on the top. And so that's why over here I've put down, like, for example, -50 for pipe 3-4, -50 because it was going against the clockwise direction. Previously, we'd done the calculations already and found, for example, 15,000, 675, -12,500, and the sum of that was 3175. We did 600, 90, 500, and the sum of it was 1190. And the correction factor, the formula for delta Q, is the negative of the sum for each loop, R times Q times absolute value of Q, divided by the sum of N R times absolute value of Q. And going through that process, we found it was -2.668 for all three of them. And so we had an adjusted 47.332, 12.332, and -52.668. Okay. I haven't yet filled in the flow rate for pipe 1-3. I did have an initial guess for pipe 1-3. Remember, my initial guess was that it would be 15. And so when I'm talking about loop 1, I call that positive 15. When I'm talking about loop 2, I call it negative 15 because it's going against the clockwise direction. And so I know it's going to be negative, but rather than put in my initial guess, which was 15, I can do better than that because I have an updated guess of what the flow rate is. Over here for pipe 1-3, I already have improved on what I think the flow rate is through that pipe. And so I'm going to say negative 12.332. So it's important that you do two things as you have a common pipe. Remember, the number one mistake students make when applying the Hardy-Cross procedure, the number one mistake is they forget to use the most recent version of the common pipe flow rate and then negative sign when you switch between loops. So if it was 12.3 in loop 1, it's negative 12.3 when I view the same pipe within the context of pipe 2. So I can go through and do these same balancing calculations, 225, negative 2450, negative 456, 30, 140, 74. Add it all up, negative 456. Okay, if I add it all up, it's negative 2681, The sum of it over here, 244. And so the correction factor is 10.99. And I have an updated flow rate of 25.99, 1.73, and negative 52.29. Okay, so I've completed now iteration 1. What happened during iteration 1? Big changes, especially in loop 2. Our initial guess was pretty bad. We had to correct the flow rates by 11, essentially, 11 flow units out of, for example, we thought that through pipe 1, 2, there would be 15 units of flow, but really, after our first adjustment, it looks like there's more like 26 going through that pipe. And so simultaneously, when we go through this procedure of adding up the sum of R times Q times absolute value of Q divided by the sum of N R times the absolute value of Q, what Hardy-Cross figured out was that if you go through that process, you're simultaneously making sure that the continuity equation is satisfied and that the energy expression is satisfied so that there aren't any preferential flow paths where the energy would be greater than or less than any other route. And so we're balancing that. And there's a link between the two loops. The reason why we have to go back and forth between the two loops is because of this pipe 1-3. They have in common pipe 1-3. And if these two loops didn't both have that pipe, then these would be two separate problems. But the reason why eventually it's going to converge is that we keep adjusting pipe 1-3, and it gets closer and closer to being balanced. When we set up iteration number 2, we'll have loop 1 and the same pipes, 1-4, 1-3, and 3-4. The N values will still be the same, 6, 3, and 5. Yeah. Oh, you know what? I was looking on the wrong row. Thank you very much. Let's see. 47, 12, 52. Okay, so 25.9. Yeah, okay. I'm really glad that you noticed that. Negative 24.01, negative 1.343. Does this make more sense? I think so. All right. There it is. Thank you. Okay, so what do you think I'm going to put in for the flow rate for these pipes? For pipe 1-4, 1-3, and 3-4. Justin, what flow rate should I use for pipe 1-4? $50 was our initial guess, but we have a better guess now. And so the main principle that you're going to keep applying is find the most recent estimate of the flow rate. And so I'm going to put 47.33. Okay. What about pipe 3-4? Well, pipe 3-4, I'm going to use negative 52.668. Because that was my most recent guess of pipe 3-4. Chase, what about pipe 1-3? What value should I put in for pipe 1-3?
Negative 1.3.
Good, you caught yourself there. So 1.343, this is the most recent estimate I have of the flow rate, but then I'm changing the sign. Because when I was talking about the flow rate here, that was from within the context of loop 2. Now I'm back in loop 1. Okay, so we go through the flow and energy balancing process and do these calculations here. 13, 442, 5.41, negative 13, 869, and the sum negative 422. Do the same thing here. So I get a correction factor. If I divide the negative of 422 divided by 1103, I'll get a correction factor and I add the correction factor to the original estimate and come up with the revised estimate. Okay. All right, so I won't go through all the balancing calculations, but what flow rates should I put in for pipe 1-2, pipe 2-3, and pipe 1-3? Bert, what should be the flow rates that I do for these three pipes?
1-2 should be 25.99.
Good.
2-3 should be negative 24.01, and 1-3 should be negative 1.726.
Brilliant. That's exactly right. So you have now a feel for how and why things proceed the way they do. What we're going to do now is relieve ourselves of the number crunching on the calculator. Think about if you actually had to do all of these by hand. I mean, it's not the end of the world. You'd be able to do it. But it would certainly take longer than when we put it into the spreadsheet. All right, so if you were going to give someone a couple of hints on things to remember as they do this process, what's the hints? Like, let me put this in a box here. What are the reminders or the tips that you think are the important things to remember? A note to yourself on the exam. What would you remind yourself on the exam here, Justin? All right, flow direction. Specifically, what do you mean? The convention? All right, so remember positive and negatives. Good. Other things to keep in mind? What other little note are you going to write to yourself in an exam? Chase? Excellent. Okay. Use most recent flow rate. If you don't, it's not going to converge, even if you make the mistake one time. Like if here in pipe 1-4, if I accidentally had said 50 instead of the 47.33, that throws everything off and it's never going to converge. So it's critical that you follow that principle of always use the most recent flow. Any other important high-profile tips? I think there's one more that we really got to remind ourselves because it's such a common mistake when we do the Hardy-Cross procedure. In fact, I'd say it's the most common mistake that students make. Bert?
Just not flipping the sign when you go back and forth.
Right. Flip sign. Is it for every pipe? No, it's flip sign for common pipe between two loops. That means that if you've got some pipe that's in both loops, when you use the most recent updated guess of the flow rate, remember that because of the sign convention of flow direction, you've got to now be considering that it's negative or the opposite flow direction as you had before. I'd just like you to watch as I put this into Excel, and then I'm going to give you a different example to try out Excel on your own. And we're not going to go through this example I'm going to give you today. You're actually going to have to continue working on Monday too, but we'll get some of it set up today. So just starting a spreadsheet from scratch, we're going to mirror the same columns that were there previously. There's going to be iteration, loop, pipe, n, r, q, r times q times the absolute value of q. There's n times r times the absolute value of q, delta q, and corrected q. Okay, we're going to have iteration 1, loop 1. The pipes there are pipes 1, 4, 1, 3, and 3, 4. Sometimes we get confused because a pipe would be called maybe 4-3. That means the same thing as pipe 3-4. Remember that the convention here is just we're talking about its ends, and so we won't get hung up if we see it written in an opposite direction. All right, and the n values for all these is 2 because we're using Darcy-Weisbach as our friction loss method. The R, 6, 3, 5, 1, 2, 3. Okay, my initial guess was that it was 50 through this pipe, 15, negative 50, and then down here 15, negative 35. I'm not going to fill in the other one yet though because that's my common pipe. Now here's finally the payoff for using a spreadsheet. For calculating this column, we just have to say equals R times Q times ABS for absolute value of Q. And here is N times R times absolute value of Q. And we can drag both of those down so that it applies it. And I'm also going to put in another little space there so that here I can have the sum of these. All right, we got the sum. What's the formula for delta Q? Well, it's the negative equals the negative of that divided by that. Now I've got the delta Q, and that matches up with everything we've done on the board so far. The thing is that I don't want to drag that formula down because if I do, it's going to be looking at the next cell down. I also don't want to anchor it because then I won't be able to copy and paste like I want to. So I'm actually going to take the time to key this in, this formula in twice, and then a third time. And that's all right. You don't usually have to do repetition like that, but in this case, it'll be worth it. And the corrected Q is just the original guess plus the difference. Okay. Now, this pipe 1, 3, the guess flow rate isn't my initial that I had, but I'm going to say equals the negative of the flow rate here. And so it automatically takes that value and gives us the negative sign. I can select these and Control C to copy and Control V to paste, and it did all the operations I wanted it to. You know, it's doing the calculations that it needs to be doing. It's summing them up in just the right way. What I do have to type in again is the formula here. All right, and so that my corrected Q, I can Control C, Control V, because it's just going to be pasting the formula, not the values, and it's going to be transposing the row that it's looking at. Okay, so it's a lot easier than doing it on the board, if for no other reason, because we don't actually have to write the numbers. Next is iteration 2. I'm going to copy all of this, Control C, Control V. All right, and I want to change a few things. First of all, this is iteration 2. And this flow rate, I don't want it to be my initial guess because, remember, the principle is use the most recent flow rate. So for that pipe, for pipe 1.4, I know that the most recent flow rate is this flow rate. And for pipe 1.3, I can just use this one, right? Right here? Right? No, thank you for saving me from doing that. It would be like walking off a cliff. I want to use equals the negative of this one, the most recent guess of that pipe. All right, and then 3.4 equals the most recent 3.4 I get from here. Now notice something. My first delta Q for loop 1 was 2.7 units of flow. Now my delta Q is only 0.4 units of flow. And so the correction I have to make is getting smaller. And that's a good sign because it means the solution is starting to converge. Things are getting better. And let's just see, this one is supposed to be this guess of flow 2.3. My most recent 2.3 is here. And this is already looking at the negative where it should. So now iteration 2 has all of the relative cell references I want it to. And if I want to do additional iterations, all I have to do is copy, Control C, make sure I give it a space. The spacing is critical. If I put in too many spaces, it won't work. I've got to make sure there's the same number of spaces between each iteration as before. 3. And look, the correction is getting just tiny, absolutely tiny. And I can do it again, Control C, Control V, and that's iteration 4. And it's essentially not making any correction anymore. So I can say that this is the converged flow rate. This is the answer of the flow rate through each pipe. And just to double check whether that's reasonable, let's have a look at what's going on at junction 3. All right, so in the final calculations of the flow rate, it says that pipe 3.4, pipe 3.4 is 52.27. And so that is negative within the perspective of loop 1, so we're going that way, 52.271. All right, what about pipe 1.3? Pipe 1.3, 1.5, and that's within the context of loop 2 being positive, so it's going to go that way, 1.512. And pipe 2.3 is a negative, meaning against the flow direction, 20.759. And so let's check that and see if continuity is honored at junction 3. In has to equal out. So what goes in is 52.271. What goes out? There's the 30 that goes out. There's 1.512 and 20.759. All right, who's got a calculator that can tell us, the suspense is killing me, if that equals 52.271 like it ought to? Bert just did it in his head, and it does, right? Justin's going to check, though, because I trust those Casio FX 115 ES. What's that? Excel agrees. You just popped it into Excel. So 52.271. All right. Flow balance is achieved, and so that's the end of the solution. I'm going to hand out an example to you now, a different example that you're going to ultimately set up and solve in Excel. But the first thing you need to do is estimate flow rates. And you don't do that on the spreadsheet. You do that by writing right on the paper with your pencil. You know, that process of guessing how much of the flow rate goes through each pipe initially. There's not just one right answer when you do this, but there is an easy approach, And that is just to split the flows equally. I'm taking the easy way. As long as you get the flow so that at each junction continuity is honored, then you will we'll all come to the same answer regardless of what our initial guess is. You could have an awful initial guess, 0.0001, and put all the rest of the flow through another pipe, and ultimately it's going to converge on the right answer. Got the flow balance there. Looks good. All right. Okay, once you get the flow balance, then you can start putting in the spreadsheet columns. But let me just discuss one thing before I turn you loose on that. And that is that in the first iteration, we don't yet know what the flow rate through the pipe is or what the velocity is. And so just to make things really easy, the way I set it up is in the first iteration, I assumed fully turbulent flow for calculating F. And then once I got beyond the first iteration, I started using the full Jane equation. And so let me show you the columns that you should put in this example. All right. Okay. We're going to actually be calculating the F values. There isn't just a fixed R. We're going to be using F values that change depending on the flow rate. And so a lot of these things are what we've already had, but there's some new ones. So the K sub S we're going to use in the F value, a diameter of the pipe, area, length. This first F value, calculating with the fully turbulent assumption, you'll notice that there's no Reynolds number term in that equation. That's the Jane equation with only the relative roughness half in there, not the Reynolds number half. Okay, then from that calculating an R value, and my initial guess of the flow rates, and then I start that flow balancing, R times Q times absolute value of Q, N times R times absolute value of Q, finding the delta Q, a correction, and then once I know a corrected flow rate, calculating a velocity, because we're going to use the velocity and Reynolds number next time when we calculate the Jane equation. So this Jane equation F value will be based on the previous iteration's Reynolds number. You know, the most recent value of flow rate that we know is what we're going to use to calculate the Reynolds number. So if nothing else, you'll have enough time today to type in these column headings, and then we'll continue on to the meat of solving it today and through Monday.